So this session is about formation of partial differential equation by eliminating arbitrary constants. So this session is about the following topics: definition of partial differential equation, order and degree, and then examples, and then formation of partial differential equations. First is the definition of partial differential equation. Definition is an equation involving partial derivatives of the function with respect to two or more independent variables are called a partial differential equation. Next is order of partial differential equation is the highest partial derivative occurring in the equation is the order of the partial differential equation. Next is degree of the partial differential equation is the power of the highest partial derivative occurring in the equation is called as degree of the partial differential equation. Next, examples of partial differential equations are, these are the few examples for partial differential equation. So if we see the first equation, x into dou z by dou x plus y into dou z by dou y is equal to z. This is a partial differential equation of first order. And in the second example, we are having both first order derivative as well as second order derivative. And in the third example, we are having first order derivative and third order derivative. Okay. So in these examples, how to find the order and degree of the partial differential equation. So first, order and degree of the partial differential equation for the first example is order is 1 because here the highest derivative is both the derivatives are first order derivative. So the highest derivative itself 1. So the order is taken to be 1. And what about the degree means the power of that first order derivative is 1 here. So that here we are taking the degree as 1. So in the first example, order is 1 and degree is 1. Next, coming to the second example, order and degree is 2 and 1 because here in this equation we are having both first order derivative as well as second order derivative. So in this the highest derivative is nothing but the second order derivative. So the order is taken to be 2 and the corresponding power to that derivative is the power 1. So we are taking degree as 1. And in the third example, order is 3 and degree is 1 because in the third example the order of the derivative is the highest order of the derivative is third order derivative we are having, so that the order is considered as 3 and the corresponding power to that highest order derivative is 1 here. So the order is 3 and the degree is 1. So next, before moving to the problem, we have to know the following notations. That is, for a function z is equal to f of x comma y, where x and y are two independent variable and z is a dependent variable. So dou z by dou x and dou z by dou y are the first order partial derivative, which we are denoting it by p and q. Similarly, the second order derivatives are dou square z by dou x square denoted by r, dou square z by dou x dou y denoted by s, and then t is equal to dou square z by dou y square. So now we shall move on to the problems. So first problem is form the partial differential equation by eliminating the arbitrary constants a and b from the following equations. So the first question is z equal to ax plus by plus a square plus b square. So this is the first question. So first step is we have to differentiate partially with respect to x and y, the given equation. So here let us consider the given equation to be equation number 1. So let us differentiate partially with respect to x on both the sides. So left side is dou z by dou x, which is equal to, here with respect to x, if you do a into 1. So remaining all the terms are considered as constant, so it becomes 0. Similarly, partially differentiating with respect to y, left side is dou z by dou y, which is equal to b. So now here by usual notation, so these are the usual notation. So here dou z by dou x can be replaced as p and dou z by dou y can be replaced as q. So likewise, so here let us denote it as p is equal to a and q is equal to b. So now we are going to substitute a is equal to p and b is equal to q in the given equation 1. So this gives you z is equal to px plus qy plus p square plus q square. So this is the required partial differential equation we have formed by eliminating arbitrary constants a and b. So the next question is x minus a whole square plus y minus b whole square plus z square. So this is the second question. So as usual here, again we are differentiating partially with respect to x as well as partially with respect to y. So while differentiating partially with respect to x, this becomes 2 times of x minus a, and y minus b whole square is considered as constant, so it becomes 0, plus since z is the dependent variable which is a function in terms of x and y, we have to differentiate it. So this becomes 2z into dou z by dou x because we are differentiating with respect to x. And right hand side, this c is considered as fixed constant, so this is going to be 0. Similarly, if we differentiate with respect to y, the first term is going to be 0, and while differentiating the second term, this gives you 2 into y minus b plus again 2z into this becomes dou z by dou y, which is equal to again right side 0. So what happened here is this equation can be written as, and then here moreover we can cancel this 2 throughout. So this becomes x minus a plus z into p using the notation. Similarly here y minus b plus z into q is equal to 0. So let it be equation number 1, let it be equation number 2, and then equation number 3. So now from equation number 2, x minus a can be written as which is equal to minus z into p. Similarly, equation number 3, we can have y minus b is equal to z minus z into q. So now we are substituting both the terms, that is x minus a and y minus b, in equation 1. So this equation 1 gives you z minus p whole square plus minus zq whole square plus z square is equal to c square. So now this is equal to z square p square plus z square q square plus z square is equal to c square. Or we can also write it as, taking z square common, we can write it as p square plus q square plus 1 is equal to c square is the required partial differential equation. So now moving to the third question. So now in the third question, z equal to x square plus a square into y square plus b square. First, let us differentiate with respect to x. This gives you dou z by dou x is equal to 2x into y square plus b square. Next is differentiating with respect to y. Dou z by dou y is equal to x square plus a square into 2y. Okay. So this can be written as, using usual notation, p is equal to 2x into y square plus b square. Next is q is equal to 2y into x square plus a square. So now from this, x square plus a square can be considered as q divided by 2y, and y square plus b square can be considered as p divided by 2x. Now put it in equation 1. So z is equal to q divided by 2y into p divided by 2x. So this is the required PDE, or otherwise further if we want to simplify, this gives you 4 into xyz is equal to p into q. So this is the required partial differential equation we have obtained by eliminating the constants a and b. Okay, the question number 2 is, form the partial differential equation by eliminating the arbitrary constants a, b, c from the following equation. So now the first question is x square by a square plus y square by b square plus z square by c square is equal to 1. So here let us start. by differentiating partially with respect to x. So this gives you 2x divided by a square, which is the first term. Second term is going to be 0 because y is considered as constant. And the third term is z square by c square can be written as 1 by c square into differentiation of z square is 2z into dou z by dou x, because z is a function of x and y, which is equal to 0 here, right hand side. Similarly, differentiating partially with respect to y, x is treated as constant, so that first term will become 0. Second term is 2y divided by b square, plus again the third term becomes 1 by c square into 2z into dou z by dou y, which is equal to right side is 0. So now this equation can be written as, we can cancel this 2 throughout. So x by a square plus 1 by c square into z into dou z by dou x, which is equal to 0. The next equation is y divided by 2 to get cancelled. Y divided by b square plus 1 by c square into z into dou z by dou y, which is equal to 0. So now let us mark it as equation 1, 2, and then 3. So now differentiating again with respect to x, the equation number 2, we will get 1 by a square, because x is considered as, if you differentiate x with respect to x, it is going to be 1 plus 1 by c square into differentiating this z into dou z by dou x. We have to use product rule. So this is going to be dou z by dou x if we differentiate z into dou z by dou x plus z into, this becomes dou square z by dou x square, because already we know what is the product rule is uv whole dash is equal to u dash v plus u into v dash. Okay, using this product rule, here we have differentiated. This is u dash, this is v, and this is u, and this is v dash. Okay, whole thing we are differentiating with respect to x, and the right hand side is equal to 0. Okay, now this equation we can replace it in terms of the usual notation. Dou z by dou x is considered as p, so p into p is p square, and dou square z by dou x square is r. So this equation can be written as 1 by a square plus 1 by c square into p square plus z into r is equal to 0. Right. Next is, now what we have to do here is we have to try to eliminate the constants a and b here. So what we can do here is, from this equation, let it be equation number 4. So from this equation 4 and from equation 2, we can easily eliminate a square from this. So from equation 4, we can write, this is equation 4. I'm writing here equation 4 is 1 by a square plus 1 by c square into p square plus z into r is equal to 0. Right? From this, 1 by a square is equal to minus 1 by c square into p square plus z into r, which is equal to c square by a square is equal to minus of p square plus z into r. Similarly, equation number 1, equation number 2. From equation number 2, equation number 2 is x square by a square plus 1 by c square into z into p is equal to 0. This is equation number 2. So from this equation, x square by a square can be written as minus 1 by c square into z into p. Or otherwise, here again, c square by a square is equal to minus 1 by x square into z into p. Now here in both these equation, left side is c square by a square, here c square by a square, we can equate it both the equation. So this gives you p square plus z into r is equal to 1 by x square into zp. We can cancel minus also. So this will be the equation here. So from this, if you want to simplify further, x square into p square plus z into r is equal to zp. So this here, this is a partial differential equation because which involves a variable as well as the partial derivative. So that this is a partial differential equation we have formed by eliminating the arbitrary constants a, b and c. The next question is x minus a whole square plus y minus b whole square plus z minus e whole square is equal to r square. Here a, b and c are three arbitrary constants and r is treated as fixed constant. So now here let us differentiate partially with respect to x on both the sides. So this becomes 2 into x minus a plus 2 into z minus c into dou z by dou x is equal to 0. Similarly, with respect to y, 2 into y minus b plus 2 into z minus c into dou z by dou y is equal to 0. So now this equation can be written as cancel this 2 and then x minus a plus z minus c into dou z by dou x is equal to 0. Similarly, the next equation is y minus b plus z minus c into dou z by dou y is equal to 0. Let us mark this equation as 1, this equation as 2 and this equation as 3. So now again differentiating equation 2 with respect to x partially, we will get 1 plus, again we have to use product rule for this term, so that z minus c into differentiating, so dou z by dou x with respect to x again gives you dou square z by dou x square plus differentiating this with respect to x gives you dou z by dou x into dou z by dou x. So this is using product rule we are doing. So now this equation can be written as 1 plus z minus c into this is r plus p square is equal to 0. Next is similarly differentiating 3 with respect to y. 1 plus z minus c into dou square z by dou y square plus dou z by dou y into dou z by dou y is equal to 0. Okay. So this gives you again 1 plus z minus c into this dou square z by dou y square is p, and this is q square is equal to 0. Now equation this, let us mark it as equation 4 and let it be equation 5, right? So for equation 4 is z minus c into r is equal to 1 minus p square. Similarly, equation 5 can be written as z minus c into t is equal to 1 minus q square. Sorry, minus 1 minus p square minus 1 minus q square. Okay. So from these two equations, z minus c is a common term. So we can take z minus c from these two equation and we can equate it so that we can easily eliminate the constant c. So z minus c into t is equal to minus of 1 plus p square r. Next is z minus c into t is equal to minus of 1 plus q square. So these are the equation. Here we are getting it from equation 4 and 5. So from this z minus c is equal to 1 plus p square divided by r. Here z minus c is equal to 1 plus q square divided by t. So now equating both, 1 plus p square by r is equal to 1 plus q square by t. So here t into 1 plus t square is equal to r into 1 plus q square. So this is the required partial differential equation we have formed by eliminating the arbitrary constants a, b and c. Okay. So here actually these two problems are, we are having three arbitrary constants a, b and c, so that we are getting a partial differential equation of second degree, which means that if the number of arbitrary constants is equal to the number of independent variable, the equation obtained will be the first order partial differential equation. But here in these two problems, we are having three arbitrary constants, but only two independent variables are here. So the resultant partial differential equation will be a second order partial differential equation. That's it for today's session. Thank you for watching.